Uh, so welcome everyone this week's Contour seminar. So let me first acknowledge our sponsors. So it's Toyota, Seagate, Mitsubishi Electric, Qualcomm, and Mossberg. We are really grateful for their support. And this week, it's my great pleasure to introduce our speaker. He's Nathan van der Moek from University of Eindhoven, Technical University of Eindhoven. I first actually got to know him because he also did some very cool experiments on connected automated vehicles about 10 years ago. And then it was, I remember my group actually had a reading group, and we read through all the papers of the competition, and it was like really nice to see, you know, people on the other end of the world and also working on similar problems we are doing here. And then soon after, we had an opportunity to meet when you came to one of the TDS meetings, right, and later for the vehicle meeting. And he was always very kind to me. And he also served as a role model for me because he's one of the people who converted from kind of being a dynamicist to a control engineer or control scientist, right? That's not an easy transition. I'm trying to do myself. I can tell you it's really hard. And then he did it perfectly. So he's very much respected in both communities these days. So you can see him on pure nonlinear dynamics conferences, but you can also meet him at CDC. So in the last couple of decades, he has been working on this model reduction techniques. And today, I guess that's going to be the main topic of his course. And I think it's nicely framed: Taming complexity, nonlinear systems, and interconnected dynamical systems. Nathan, the floor is yours.
Okay, thank you very much, Gabo. First of all, thank you for having me here. It's great to see so many people showing up on a Friday afternoon. If we would do that in our group, we would have a tough time, at least without cookies. And thanks a lot, Gabo, for hosting me this week. It has been a great pleasure to visit you. So indeed, I want to tell you more about, so this talk will actually not be about control, but I think it should be interesting to a control community. So it's all about model reduction, which means how can we reduce the complexity of the models that we use, either for design of engineering systems, for control, diagnostics, etc. So I want to, bit of an outline for the talk. First, I want to motivate why is this at all an interesting topic. And then I want to address the problem both for reducing a class of nonlinear dynamical systems, and then I will talk about reduction of linear systems, but what if we have many of them interconnected? How do we think about complexity reduction in that case? So, yeah, complexity is everywhere. I want to start with one example from our region. So the Eindhoven region, we call it the Brainport region. It's well known for high-tech system manufacturing. And one of the big companies is ASML. They have 95% of the world market in chip manufacturing machines at the moment. They make machines like this. They're 120 million euros, and they are larger than a big bus. Yeah. So they actually make models of the vibrational dynamics, thermal dynamics, fluid dynamics, to secure the performance of these machines. And they're saying, yeah, the models that we build, they're too complex. We cannot use them anymore for our design process. But you can also think of models in, let's say, worldwide multimodal logistics. You can think about neural brain dynamics. Our power grid are all examples that if you try to model them in a more integral fashion, then very quickly models blow out of proportion. Now, you could mean many things with complexity. Of course, you could think about behavioral complexity. The model might be simple, but I still have very complex behavior. Complexity in more networked interconnected system sense. I think of the power grid consisting of many nodes or many neurons here or many components in this system. Or you can think about complexity, the number of states or variables that you need to describe the behavior of your system, states of your state space model, for example. Or it could be heterogeneity, that the system has a lot of multiphysics or maybe even cyberphysical aspects. Now for today, I mainly want to talk about this. What if your state space model gets a lot of states. I will also address to a certain extent the second part. Okay, then also models are everywhere. And I think now in these days, where the word of digital twinning is already getting old, but well, in this scope, people have the ambition to model systems in an increasingly integral or holistic manner, kind of getting all the facets that play a role on board. Yeah, that increases also the complexity of these models. And at the same time, we want to use these models in real time, for example, for diagnostics purposes. So computationally, we should be able to actually do analysis on those in real time. Now, actually, typically the model dimension then obstructs either numerical analysis simulation, design optimization, controller design on the basis of these models, or diagnostics, for example, fault detection. So I would say model complexity reduction is really a key technology for the future design of complex engineering systems. And so this is for me the motivation to look into this. So what is model reduction? So this is a picture I stole from a math professor at our university who worked on model reduction for decades. So clearly you recognize what it is. And I would say this is a very complex model of a rabbit with many facets describing its surface. But I guess if you would have seen this, you guys would also have recognized the rabbit. So this is the essence of model reduction. Can you describe it by less variables or parameters, but still catch the essence of what you need? Right? Okay, now what is the goal in model reduction in the scope of dynamical systems? Of course, reducing model complexity. In this case, we talk about reducing model order, while of course, preserving some level of accuracy, where immediately accepting there's always a trade-off between complexity and accuracy. You might want to preserve structure. If your system consists of multiple interconnected systems, then after the reduction, you might want to be able to still see that structure for interpretability or scalability. And we might want to be preserving system properties such as stability or passivity after reduction. Okay, so again, I will now first start talking about model reduction for nonlinear systems and get to the second topic after that. So model reduction for nonlinear dynamical systems, that has been a topic which has been around for quite some time. So the literature is quite diverse. You can think about model-based approaches where you really have a description of your model, typically in terms of differential equations at hand, and you want to use that vector field or system matrices as the basis for doing reduction. Data-based is you either have a lot of snapshot data from simulations of a high fidelity model, and you use that data to construct the model directly. What I'm talking about today is more in the top category. And I'll mainly focus on balancing type techniques and moment matching techniques as a basis. So most of the existing work on balancing and for balancing a nonlinear system, this was the original work of Jacqueline Scherpe. And in 2010, also Alessandro Astolfi extended moment matching techniques for linear systems to the nonlinear context. But the focus is on local results. So this means that what they were doing is constructing lower dimensional representations of nonlinear dynamics near equilibrium, which also means if you have perturbations that excite the system, they can only be small, so you have to stay close to this equilibrium. Otherwise, these reduced order representations were not accurate. What I want to do here is to get rid of that limitation. Now, so we want to go global. What if you have excitations that bring your system far away from an equilibrium if you don't have excitation? Well, clearly, nonlinear systems can have all kinds of attractors, multiple equilibria, limit cycles, or even worse. Now, then I start to think, what do you actually expect from model reduction if you have that complexity? Is that actually a problem that I would like to tackle? Well, if you would want to, then you would have to think about preservation of the number and the type of steady state solutions, the accuracy of those, the accuracy of the transients and their stability properties, maybe even preservation of the basin of attraction. I honestly would not know what that would mean if you go to a reduced states or the state space and preserve the basin of attraction. So for me, these were actually highly complex challenges in the general context. So that for me motivated to look at the problem setting where the nonlinear system has unique, stable, steady state behavior. So that there is only one attractor which all solutions converge. And this motivated for me to exploit so-called incremental stability type properties in the reduction of nonlinear systems. So that's what I'm going to exploit. And I also want to, I kind of advocate that actually helps to get quantitative error bounds on the accuracy of your reduced order model and a way to preserve stability properties. Okay, so let's then dive a bit more into the technical part. So the generic problem setting is that we have an original system, here I denote it by sigma, given by some nonlinear differential equation with state x, input u, and some output y, where this dimension n is typically large. It's a high dimensional state space. Then the reduced order model that we want to construct, I denote by sigma hat. It has a state x hat, another vector field f hat, and another output equation h hat. And now the state dimension is small, or at least significantly smaller than n. Now, what we typically want is that if we excite this system with the same input, u, and we look at the difference between the outputs, that's the reduction error, that this error is small. And that's what we mean by accuracy. And on top of that, we want to have preservation of, for example, stability. And preferably, we want to have a bound on this reduction error. So a quantitative bound that can tell you your error will never be larger than this. And we want to do this not only locally for small inputs, but for any bounded input that you might want to provide to your system. Okay, now I'm going to look at a particular decomposition of the dynamics, and I want to motivate why this is actually relevant because it constrains the class of systems that we're looking at. So we want to look at systems which consist of a linear part, a linear, very high dimensional state space description, with a linear, potentially dynamical system, a nonlinear dynamical system in the feedback loop, which is of relatively low order. Now, this actually arose from many applications that me and my colleagues worked on. In these systems, many of these components can be described by linear finite element models that arise from finite element discretization, which are just linear dynamical systems. But on the interfaces, that are cables, bolted connections, frictional joints, all kinds of local nonlinearities. These suspension bridges, if you're in civil engineering, the bridge deck could potentially be described by just linear dynamics, but these cables might be represented as one-sided springs because they can only be loaded in tension, which act only locally on the bridge deck. So there are many examples in which you get models which are actually of that form. Now and then, typically what people in industry do is the following. They don't think about reducing the entire system. They just pick, for example, this finite element model, the linear part, reduce the linear part, keep the nonlinear part intact, and just reconnect that nonlinear part. So now we have a linear system here. This is the linear system. We have a nonlinear system which has a lower dimensional state Z. And the only thing we do is now we only reduce this left linear part and keep this right part intact. So the same vector field here, same output equation. But the question actually is, this might be engineering practice, but why is this actually a good idea? Or when can you actually guarantee that you don't destroy stability of the system, that you get bad accuracy? Under which conditions can we actually guarantee that this works well? Okay, now this I actually already said. This is just how we do it. I already said that this is commonly used in engineering, but it's also a computationally attractive way of doing things because the reduction of this linear part, there are many model reduction techniques for linear systems available. Also computationally, it's advantageous. Now, next, I want to exploit so-called incremental system properties of this nonlinear feedback system for several reasons. It will help us to derive an error bound. It will help us to preserve stability. And it helps to guarantee that we have unique steady state solutions for any bounded input that we provide here, any bounded input U. So this misery of multiple attractors, which might have basis of attractions that we don't know how to approximate, that problem is not there. So what I need to do first is now to introduce the incremental system property that I'm going to require in this context. And that's called convergence or convergent systems. That was actually arose in the 1960s in the Russian literature by Demidovich and other colleagues. So let me define this property first. So maybe first this picture, you have a nonlinear dynamical system with state x, some time varying input, u of t. And this system is called convergent for a whole class of inputs if we have two properties. One, there should exist a solution denoted by x bar u of t, which is bounded on the entire time axis from minus infinity to plus infinity. And the second property is this solution is globally asymptotically stable. So in this picture, this x bar u of t could be this gray solution here, which extends in forward time and in backward time. But all other solutions for any other initial conditions forward in time converge to this solution. Now we call the system, we have some adjectives here, uniformly or exponentially convergent, if this solution has uniform or exponential stability properties. Now we call this x bar u of t the steady state solution because this is the bounded solution to which all other solutions converge. And if the system is uniformly convergent, we can also show that this is unique. It's the only bounded solution on the entire time x to which all solutions converge. Okay. Now I need one more extension of this property, which is a combination of convergence and input to state stability, which is a robustness property under input perturbations. So let me try to explain this. So this system is called input to state convergent if these properties hold here. But what we're going to consider now is we have our system with a nominal input, u of t. That's the input here in the white line. And it generated a steady state solution in white here. Now, what is going to happen with our solution if we perturb the input a little bit? So we go from u to u tilde. Now, this system is called input to state convergent if it is convergent or uniformly convergent, as I just defined. And this inequality is satisfied. And this is basically input to state stability with respect to the time varying steady state solution here in white. So it says, if we change the input from u to u tilde, so this is the perturbation in the input, then we can bound the difference between this white steady state solution for the nominal input and the total solution for a certain initial condition of the perturb associated to the perturb input x tilde by a class k function beta, which goes to 0 over time, depending on the initial condition difference, and some class k function of a bound on this input perturbation. So in other words, if I perturb the input a bit, then all solutions converge to a small bound around the steady state solution of the original input. Yeah, that's input to state convergence. Okay. Now, so now back to model reduction. So now I'm going to introduce a few assumptions that we need to make statements on accuracy bounds on model reduction, stability preservations, etc. So the first assumptions are on the original system. Now, the first assumption that we make is this sigma lin here, this linear system, is asymptotically stable. Now, any stable linear system, asymptotically stable linear system, is also uniformly convergent, is also input to state convergent. You get all those properties for free in the linear context. Now, that also means that we can write a bound like this. So let me first define this. This f here is a steady state output operator. So this x bar is the steady state solution to which all other solutions converge because the system is convergent. And this is just the output. And Fy means the steady state output y, and Fw means the steady state output w. Now, if we take two different input pairs, U1 and V1 and U2 and V2, then we get different outputs, right? If you change these input pairs. And this tells you that if this system is input to state convergent, then the difference between these steady state outputs, here an L infinity norm, is upper bounded by something related to the difference in the input U and the difference in the input V. Now these gammas are gains from input to state, from V to X and from U to X. And this chi is from state to output, where the I is again the two different outputs. So you can bound how perturbations in inputs go to perturbations in steady state outputs. That's all this equation says. Now the second assumption is this nonlinear system is also input to state convergent. So this means we can also write down such incremental condition on the steady state output. So GV is now the output of the nonlinear system in steady state. If we perturb the input to the nonlinear system a bit, W, then the output is upper bounded the difference by this function where we again have an input to state gain and a state to output gain. Okay, these are two assumptions. There's one more assumption that we adopt, and which is basically an incremental small gain condition for this feedback control system, or yeah, that's feedback interconnection, sorry. So it might look complex, but let me just get rid of these functions rho. If you look at this, this is just applying the different gain functions that play a role when you go through this loop. You could start at V here. Then the gain gamma here is the gain from V to X of the linear system, then from X to the output of the linear system. W is the input to the nonlinear system, go to the state of the nonlinear system, etc. This is just an incremental nonlinear small gain condition. Now, you can show that if you satisfy these conditions, then also this entire feedback interconnection has this nice input to state convergence property. So now under these conditions, our original system for any bounded input has a unique steady state solution to which all other solutions converge. Okay, now if you have a simpler case where this sigma NL is a static nonlinearity, many cases where this is the case, and you have a decentralized static nonlinearity, then this condition that I've posed here, you can get it by just the well-known circle criterion conditions for Lura type systems with incremental sector conditions on the nonlinearity, for those of you familiar with absolute stability theory. Okay, then we need a few assumptions, which will later prove on not to be assumptions, on how we do reduction. So we're only going to reduce this linear system here. Now, one assumption is we reduce it in such a way that the reduced order linear system itself is asymptotically stable. And the second is that there exists an error bound on this reduction. And so here this epsilon I, where again I can be related to the two outputs, are the steady state output operators of the error system, the difference between the original linear system and the reduced order one. Now this is just an incremental condition but because this is linear, we can't forget about all of the U1s and the V1s if you wish. It basically says you can upper bound the steady state error by an error gain related to the first input plus an error gain related to the second input. So these small epsilons are error gains. Now this can straightforwardly be satisfied if you employ balanced truncation or balanced residualization or any balancing related method. They typically give you these properties, that you preserve stability and that you have this error bound. And typically these epsilons are related to the singular values that you throw away after balancing. And so we can very quickly compute it even without doing the reduction itself. You can compute them before doing the reduction, only by deciding on the reduction order. Okay, then the result is the following. If we satisfy these conditions and this robust small gain condition, so if you now for the time being forget about this epsilon here, then we have the original small gain condition for our original high order system. This is in that sense a robust small gain condition because it has to hold. Also, if we put an additional error here, which actually tells you what is the error. Let me now go back to the picture. In the transfer function from V to W by replacing the original dynamic system with this approximated one. So you only need that error bound on that transfer function. Now, if you satisfy this robust small gain condition, then what you get is that your reduced order system also has this input to state convergence property. So still stable for any bounded input, no matter how big it is, the steady state solution you get is unique and asymptotically stable globally. Now, and you can compute a steady state output error bound. So if we define the steady state output error as the difference between the output of the original system and the reduced order system, then it satisfies this inequality. So its L infinity gain is upper bounded by an error gain epsilon times the L infinity norm of the input. And this epsilon, it's a complex expression with all these gains here. The most important thing here is all the gains gamma and chi that you see are of the original system. And all the epsilons are the error gains of the linear reduction. Now, two things are important. You can, this epsilon, you can make small by making these small. So you can always make it smaller by making you can make the reduction, the nonlinear part, more accurate by making the linear reduction more accurate, which makes sense, right? And you also have a mechanism of making this small such that you can always satisfy it by reducing less. And you don't need to do the reduction yet. You can assess this before you do the reduction to decide how far should I reduce. Maybe you have a certain requirement on your accuracy. And then this gives you a way of thinking about to what order should I reduce to be able to satisfy this accuracy requirement. Okay, yeah, so before I told you, yeah, one way to satisfy the conditions that I use here is using balancing-based methods. Now, another very popular method in linear model reduction is moment matching. Basically, I only have one slide. It basically says you can do exactly the same thing with stability preservation and error bounds when you want to use moment matching techniques for reduction. Now, for those of you not familiar with it, moment matching, what it does, if you think about just a linear system, single input, single output, this is the frequency response function. In blue, the original one, moment matching, what it does is it creates a state space, a reduced order state space representation, where at specified frequency points, you exactly match the frequency response function. Now, there are additional techniques that then say, yeah, now I'm not happy because this red one, yeah, might match at these frequencies, but outside it, it's actually quite poor, right? Now, there's still always freedom in that state space representation to require additional properties, stability, for example, but also optimality in terms of the difference between the red and the blue one. And by doing that, you can go with the same order, you can go to the yellow one, and to also get a better description in between the so-called interpolation points. Now, you can use this for the reduction of the linear part, apply the same type of conditions I introduced, and you get the same type of result. And so you can have a relatively broad class of reduction techniques on the linear side for which you can extend it to this class of nonlinear systems. Okay, a simple example. Because I cannot show you some of the examples of our industrial partners. So this is a very simple mechanical system. I think in the example, I take 100 degrees of freedom. It's all linear, mass spring damper system. There are only two nonlinearities. There's a nonlinear spring here and one here. And the blue one in this case is a saturation nonlinearity, and the red one is a dead zone nonlinearity. Now, so here I applied both approaches. So we reduced the system from 200 to 11. We checked all these conditions. So we're guaranteed to have stability preservation. We have an error bound that we were happy with. And here you see the frequency response functions and their approximations. In black, the original ones. So this is for different inputs to different outputs. Now in red, you see the balancing-based frequency response function. In green, the one obtained from moment matching. They're different. But both have these guarantees. And if you now you give some bounded input perturbation here, then you get in black the original response, and in colors, the two approximated ones, and here the errors. And here there are zoomed in pictures that you can actually get quite accurate matching of the response signals. Thanks. That's just one example how you could apply this. Okay, this is all I wanted to say about reduction for a class of nonlinear systems. I want you to remember one thing is, if you want to think about model reduction for nonlinear systems, it's really useful to impose incremental stability properties, both to be able to prove that you preserve stability and to get an accuracy specification or guarantee. Now, the next part I want to talk a bit, so in certain sense, this was already about model reduction for interconnected systems because we had a linear and a nonlinear part. Now I want to go, what if we don't have nonlinearities, but we have many interconnected linear systems, and we want to reduce this total dynamical system. Now, why is this relevant? Again, some examples. I know some of you are in automotive engineering. I think, yeah, a car has many parts, right? But also these chip manufacturing machines have many modules, and many of those modules are actually designed by different teams. And these different teams make their own models. And they actually want to be able to reduce them individually. Or first, if they put them together, the model is maybe 100 million states. That's the order you have to think of. Totally infeasible for anything. So they have to reduce this. Of course, aerospace industry, I guess these models are typically also very large, and you also need some form of model reduction. So the complexity is, and the high order nature of the subsystem models, and the complexity of having an interconnected system. So what is the problem? Now, given some interconnected system which consists of different subsystems which have linear dynamics and some interconnection structure, we want to find a reduced order system that, of course, approximates the input-output behavior, preferably again with an error bound, preserves system properties such as stability or maybe even passivity. And this is the most important one. We want modularity, such that if we reduce the system, then after reduction, people can still recognize, this is the red part, this is the blue part, this is the green part. That we still can interpret what these sub-models still represent. That also makes it computationally feasible, because this means that we will be reducing individually the red, the blue, and the green part, not the system as a whole. Applying model reduction to a system of 100 million states is not feasible to begin with. Okay, now, this I just said. If you can reduce the system as a whole, which is often not feasible, it's typically the best thing you can do from accuracy point of view. But it also destroys totally the modularity structure. You will not recognize what the subsystems were after reduction. So that's why people started working on structure preserving methods where you still recognize the different subsystems. Now, the benefit of that is that you do have modularity, and you can still interpret after reduction which subsystem does this part of the model represent. It is computationally feasible, and the other nice thing is maybe some submodels are coming from vibrational mechanics, other from fluid dynamics, other from thermal dynamics, and each domain might prefer their own model reduction strategy. So this allows for that heterogeneity. Now, the open challenges are, there are typically no error bounds. There are some exceptions which are quite conservative. But the main question is, how do we specify requirements on the accuracy of the subsystems such that if we adhere to those specifications, that we get the desired accuracy of the interconnected system? Now, and in that perspective, you have to realize that if everyone is doing the reduction from their own perspective in the subsystems, typically it does not lead to the best reduction for the system as a whole, because there is interconnection in the dynamics. Now, this is a bit of a picture, just kind of graphically display the challenge. So now suppose you have different teams here that are designing parts of the system, a robot, some transmission, there is maybe an electronic components, and they're all building their models to support their design. Or let's say, these are the high fidelity models, and they here construct their reduced order models that are more effective for them. But obviously, there is an error between these models. So let's call the errors here epsilon 1, epsilon 2, epsilon 3, or maybe it's better to think about these epsilons as error specifications, saying this tells something about how accurate I want this reduced order model to be. And then we have epsilon c, which is the accuracy requirement on the total system. Now I want to consider two kind of approaches or problems. One is, if I specify an accuracy specification for the subsystem models, can I compute what the accuracy guarantee is for the interconnected system? That's one question. The other is, the other way around is even more interesting. If you would give me an accuracy requirement for the total system, I want the total model to be this accurate. Then how can I determine how accurate the subsystem models should be in order to guarantee this? Because that would distribute these tasks to the individual modeling teams. Okay, so this is going to be quite conceptual, but a few equations are needed. So we describe the LTI subsystems by transfer functions Gj. and we collect them in some diagonal block of transfer functions, which we call GB. Now, then we have this interconnection structure we represent by some interconnection matrix K here to get the fully interconnected system. Now, then we might still want to introduce some input and output matrices to make sure that we identify the performance inputs and outputs that are important for us in this model. Now, then we get an interconnected system model, which we call GC, which contains all these blocks. Now, of course, GC we can represent by this transfer function. And in the reduction, the only thing we do now is we're going to reduce all these individual subsystems to their reduced order variance. G hat could be with balancing, with moment matching, whatever you would like. Now then, this matrix GB changes to another diagonal matrix of all these reduced order transfer functions. And we get a reduced order interconnected system model. And so the only difference between the blue and the green is there are reduced order transfer functions here. Okay, now then we can also define an error dynamics between the two. So if we now say we feed the same input to both the original and reduced order system and look at the error between the outputs, then the error transfer function is just on subsystem level, EJ, the difference between these two, and on the total system level here. Now, and here you again see these kind of error specifications for a subsystem and the total dynamics, EJ or epsilon J and epsilon C. Now, the only thing we do is a very conceptually simple thing to use tools from robust performance analysis that quite many of you probably know. If we just represent the error that we are making by reducing the order of the system by some weighted uncertainty. So here this uncertainty is just this delta is a norm-bounded uncertainty. The V and the W are just weighting functions. So now we represent this reduced order system by the original one plus this uncertainty path here. Now, if we then put all these weighting functions and these uncertainties in some diagonal representation, yeah, then we can actually represent the reduced order model in terms of all the matrices of the original system and these weighting functions and uncertainties. Now, the last step is simply, this is the same picture as before. So this error dynamics is just the error we get by supplying the same input to both the high fidelity and reduced order model and looking at the difference. And also that error dynamics now only depends on the matrices of the original system and this uncertainty. You see now by replacing the G hats by this feedback or this uncertainty representation. Now we can simply, in the yellow block, this parallel interconnection of these two models is just some kind of nominal system with an uncertainty. So if we just, here you recognize a standard problem setup that you would also look at in robust performance analysis. So now the concept of a structured singular value can be used to actually relate these epsilon J's and the epsilon C. Yeah, a bit more specific. So we typically want to use frequency dependent performance specifications. So our performance specification here would be for the subsystems, the error dynamics would be such that their weighted variant has this norm bound. And on the total system, we have something similar. Now then, yeah, using these standard results, you can say for any set of errors on the individual reduced order models that satisfy their specifications, we have that the interconnected system satisfies its own specification. And that can be checked by just looking at this singular value. So it's just using all the tooling you know from robust performance analysis or robust control, but now just using it in a different problem context. Okay. Now, one thing I think is important to mention is the problem that you need to solve on the previous slides is not related to the dimension of the state space models. It's only related to the dimension of the interconnection structure. So these models can be 100,000 degree of freedom. And then the problem you need to solve for can still be small if the number of inputs and outputs are more modest. And we can guarantee that we also preserve stability if we satisfy these conditions. Now, then we can solve two problems. And I want to give two examples here. This bottom-up problem. So given accuracy requirements on these individual systems, can we predict or can we compute an accuracy guarantee for the system as a whole? Now let's again look at a very simple system here. Two flexible beams interconnected by some flexibility. Both are of order 100. They're going to reduce to an order 10. Now the total input-output transfer function from some input here to some output there is given by this dynamics. If we would just reduce to order 10 both with balancing in this case, we would get the red transfer function and the error would be something like this. Now, with our method, actually before constructing this reduction, we could guarantee with the error specifications for the two errors of these reduced order models, we could predict that the transfer function that we would construct for the total system, the error would be below the red part. And indeed, it lies below. And you see it actually quite nicely follows the actual error. Now, if we go to a frequency independent error bound, then we get the green error bound, obviously. And previous results were only able to give us a quite more conservative error bound. So this just means we can quite accurately predict what the accuracy specification is, again, without actually doing the reduction. So you can do this for many different orders, check this, and see when you're happy, and then do the reduction. Now then, the more interesting problem even is top-down. Given some requirement on the total accuracy of the system, can we specify the accuracy requirements for the subsystem models? Now, similar example, but now three flexible beams also interconnected by spring damper combinations. Now, this interconnected system has this transfer function from an input here and an output there. Now, in total, these are the orders of the original dynamics. So in total, now we have 400 states. Now we're going to use this approach, and we first pose a requirement that the error on this transfer function can be, in this case, 10% of its original magnitude. It means that if we reduce, the reduced order transfer function should lie in this gray area here. So in this gray area. Now, how do we have to reduce the green, the blue, and the red in order to get this result? So let's say the error specification is now the error on the total system should be below in this gray area. Now, this framework allows us to compute error specifications for the three subsystems. This tells you the error for the green beam should be below this, for the blue one below this, and for the red one below this. This we can actually feed or used to design weighting filters for frequency weighted balancing to really guide the reduction such that you specify these, or you guarantee, satisfy these specifications. So now we did this. We do the model reduction. For the green part, we reduce, and we find indeed a model that satisfies this error specification. The same for the blue, and the same for the red. And then if we look at the error for the total system, then you indeed see now it's automatically guaranteed that the real error is below this error specification for the system as a whole. And we have reduced by a factor 10. So this makes actually this whole thinking about who should reduce how much, it really gives, it's really a helping hand to give the right specification to each modeling team. So kind of, we call this a contract-based approach for model reduction. Right? So you make agreements between different subsystems or the teams working on this, who should reduce how much to satisfy our overall goal. Okay, then I want to wrap up. Maybe a bit of outlook. On the results on nonlinear systems, I introduced this convergence property. You can do exactly the same thing if you want to preserve incremental L2 gain or incremental passivity. There are the same results are there. We can also do optimal moment match for Lure type systems. There's very interesting work of Yuka Wano and Bob Besseling on how to use the nature of the nonlinearity in the reduction itself more. I started complaining about that the case of non-unique steady state solutions is very complex. There is some very interesting recent work of Alberto Paduan in the first step in that direction. And the same type of reasoning we have also used to develop reduction methods for delay differential equations and for sample data systems, if you're interested. I don't know how much time do I still have to, no time?
Probably.
Then I'll skip this. Well, two things. I want to acknowledge my co-authors. And if you're interested in this material, just last week, an overview paper in the annual Previews in Control has appeared where all this type of material is in. So that would be your best entry point. And I want to thank my co-authors and students at TUE, and also collaborators at NTU in Norway, at Imperial College, and at the University of Cornell. With that, thank you for your attention. I'm sorry if I took more time than anticipated.
Thank you for this very interesting talk, and the floor is open for questions.
For the one where you changed the overall epsilon into 3 different ones, how unique is that decomposition? That my intuition would be that you can also allow one of the subsystems to have more error in exchange for another one having less, right? So
that's a very good observation. So that problem we did not solve yet. You're totally right that to guarantee the accuracy specification for the total system, there are many ways how to distribute the requirements to the subsystems. So we picked one, right? But maybe it could have a higher requirement on the one, could have relaxed on the other. So a question is, how can we actually optimize that? But then you have to put in some additional requirement, right? So is it more difficult for one subsystem to reduce or not? Or are they locally losing too much accuracy? So you would have to define an additional optimality criterion to pick the right one in that whole space of options. Yeah, you're totally right, it's not unique.
Is it easy to add, or like if some engineers told you the relative difficulty, then would it be easy to just like add some penalty, or would it up the process?
I have no idea. I think it highly depends on the optimality criterion that you put, right? That will define that optimization problem.
So I would have a question. So you showed a couple of examples, with reduction, and then you said, oh, we have 100 degrees of freedom. Let's make it 10. So why 10? Why not 2 or 4? Like, how do you choose these numbers? I understand in the example it could be anything, but more precisely, like, what would be the guiding principle? Like, I choose these reduction.
Yeah, so in these examples, one way to look at it is go to one of the pictures. So here it could be, so here we reduce to order 19, and you see, why 19? Now, probably my student picked it such that if you pick 20, yeah, or the balancing method that he used, he didn't guarantee this anymore. Yeah. Oh, sorry, if you pick 18, sorry, if you reduce more, you would not satisfy them. But if you go to 20, yeah, then you also specify it, but you leave your model more complex than needed. Yeah. So you pick the lowest number such that you still satisfy the specification to have the best balance between complexity reduction and still satisfying.
And in this case, these frequency bounds, basically they are uniform. Like, so they always say, like, we always 10% within the original frequency response.
No, this is totally up to you. You could pick any frequency dependent specification that is important to you. Maybe you are saying, I find dynamics in the 0 to 500 hertz extremely important. After that, I don't care.
Mm-hmm.
You can, this gray area is totally for you to design.
Mm-hmm.
There's, in that sense, no restriction.
Thank you.
So fascinating presentation. Thank you very much. Very nice ideas. I learned a lot. I appreciate it. I have a question related to one of the common criticisms in reduced order modeling, which is that the cost of building the reduced order model is more expensive than actually solving the full order system. So in that context, if all I want to know is the frequency response function of the complex system, what would be the relative cost between actually using the full order model to do the frequency response function versus the effort to build the reduced order model and then use the reduced order model to have the frequency response function? Are they equal? Is there a gain in doing the reduced order model if I have a one shot or one calculation need?
I don't think that there's one answer to it. There are many methods, different methods, and the one is more efficient than the other to construct a frequency response function for a very high order system or to do a reduction. And the one method has another computational load than the other. I think the key is, if you really need to do it once, yeah, you can also analyze the high order system, right, if feasible. But if you have to do an analysis on that system a lot of times, right, or in real time continuously, and it's better to do the reduction once and then being able to use that reduced order model time and time again, then it pays off to do the reduction.
So for example, here to build this reduced order model from 200 to 19, what was the computational cost versus the cost of calculating the frequency response?
So here it would be comparable. It probably is faster to compute the frequency response function, I would say. I mean, these are low orders.
Expensive, right?
Sorry?
The balancing methods are expensive, that's right.
They are definitely on the expensive side for the reduction methods. Yeah, absolutely. No, so here, I mean, also this comparison, because the other academic examples, yeah, do not really make sense. But if you go to really high orders, so really with this industrial company, we're looking at millions. And then we're also not using the standard balancing methods anymore because that doesn't fly. Yeah, then just the obstacle of not being able to reduce the system as a whole becomes an argument, right? So you have to decompose, you have to do something in reduction. And also if you keep, let's say, you keep a few thousand and you would like to use robust control synthesis methods, they will not be happy with the order of the controller typically, right? And then you can argue, should you do model reduction, then controller design, or should you just try to build a controller, reduce the controller? That's another story, but you need to do reduction somewhere for those type of application purposes of using models. But I totally understand your question. Fair point.
To the interest of your Friday afternoon, let's stop here and thank Nathan again. Thank you very much.
I knew like specifically about the security incremental and whatnot. The thing is, oh yeah, it's just tough. This is really hard. There was they looking at TV and the way that I
Intuition. Makes sense. I can get that intuition behind.
that they're just.
Very familiar.
Yeah. I saw like vehicle dynamic and blah blah blah. I don't know. It's a model. Think about it. 20 million is a freedom per sector of I'm going to ask you if you're doing this structural dynamics or are there other non-second order systems? A lot of
That they say.
Someplace in central.
more tractable. Otherwise, balancing is fantastic, but it's so expensive.
Actually, I was able to take it yesterday. It was able to be. Yesterday, I was.
Thank you, Sebastian, for me.
I'm looking for maybe I'll read the paper.
Yeah.
Nice. We are improving.
Thank you for visiting. We pass, I go through.